Hi, I'm Ben Canning, and this micro-lecture is on parts of a wave. As always, you need 3 or more bullet points worth of notes, 1 to 2 sentence summary, and your follow-up questions on Google Forms. Okay, so generally speaking, there are 2 ways to graph waves, or 2 ways that we normally do it. The first way is a time graph, meaning we use time as the x-axis, and the second way is a distance graph, meaning we use distance as the x-axis. Now, each way shows a certain type of information, but each way is also missing a piece of information. We're going to go through that now. Alright, so we're going to start with the time graph. In here we've got time on the x-axis, and we've got displacement on the y-axis, and we've got kind of a sinusoidal looking wave going through here. Now, the first part to teach you are the crest and the trough. Now, the crest of a wave is just the top of the wave, and the trough is just the bottom. We call it a trough because if you notice this kind of bottom half here, looks a little bit like a bin or a food trough. In other words, kind of that like long stretch tub kind of looking thing where people used to feed animals from, and probably still do. I just don't see that often anymore. Alright, next part is equilibrium. Now, equilibrium is the resting position when there is no disturbance. Meaning, if there was no wave or disturbance coming through here, what would the water or air or whatever this is, what level would it be at? And we can see that the kind of ups balance out with the downs, and that the equilibrium would be right here in the middle. Now, displacement is the distance from equilibrium at different moments in time. So at this moment in time, the displacement is represented by this arrow. Here, it's represented by this one, and here it's this one. So the displacement is constantly changing with time. So if you imagine one thing, it would just be kind of going up and down, up and down, up and down. So displacement is the distance from equilibrium. Now, amplitude is just the maximum displacement. Now, I've used this kind of horizontal line to represent it, but really it's just this guy right here. So we've got the maximum displacement is the same at this one, and here as well. And that is called the amplitude. And usually we refer to it as a positive number, even though it's equal and opposite in the negative direction in this case. It doesn't always have to be, but it is in this case. Alright. Last but not least, one cycle is one complete wave. So here we can see that one portion or one complete cycle of the wave, one up and one down, is represented by kind of this red part, or we could also identify it as going from here all the way to here. And we can see that this entire wave representation has a couple of different cycles in it. So it looks like about 2.5 cycles or thereabouts. So one cycle is just either this part of the red or this part in the blue. Really, the way I identify it is it's the space in between where the wave repeats. So it goes from here, goes up, goes down, and then at this point it repeats again. And this red line goes a little bit past where it should. Now, it's important to know what one cycle is because that lets us determine the period. So in this case, on a time graph, we can use one cycle, and we can see that one cycle occurs in 4 seconds, and so the period for this wave would be 4 seconds. And from that, we could use the inverse of that to figure out that its frequency is 0.25 hertz, or 1/4 of a hertz. Now that's it for a time graph. But let's look at a distance graph, because time graphs show us about period and frequency, or we can figure out frequency, but they can't show us wavelength. And similarly, distance graphs can show us wavelength, but they cannot show us the period or the frequency. So let's go to a distance graph. Everything's the same so far on the distance graph in the sense that the displacements and the amplitude can still be determined. We can still see that one cycle is right here, so one up and one down, but the distance traveled in one cycle is what wavelength is going to be. I also like to think of it as the distance between crests, so one crest to another crest gives you the wavelength, but really it's just the length of one complete cycle of the wave. Now this graph looks the same, but we notice that it's a distance graph instead of a time graph. So in this case, the wavelength is 2 meters. Now, the last thing that isn't shown on either graph is wave speed. And wave speed is just how fast is the wave traveling, meaning how fast does this wave right here reach this bird over here. In this case, it shows it as traveling at 2.5 meters per second. So just think of this as how fast does the wave come towards you or move through space, etc. But remember that it is only the energy or disturbance that travels and not the actual like water itself. That's it. 3 or more bullet points worth of notes, 1 to 2 sentence summary, and do your follow-up questions on Google Forms.